volume of revolution, cylindrical shell. So earlier we calculate the volume by first calculate the area of the region, and then we rotated it about the x-axis or the y-axis or whatever axis of rotation that we have. So here the idea is that if we are given a function f, and we will calculate the area by pureness by layer. So what do I mean by that? So let's say you have a cylindrical, a cylinder, okay? And the cylinder you divide into ring. Okay? You slide into ring. Think of an onion. You slide into ring. Then we say that we can calculate the volume of each of this ring. The volume of each of this ring. Let's say if I just slide the straight in half, just take a slide, take it out that way, and we roll out that slide. Then we have a rectangle with a tiny, height that we call it. Okay. And we can calculate the volume of this little box, the sheet box here that we're gonna have with a very thin sheet. Okay, we can calculate that volume. Now we keep on sliding that cylinder to get each of the small sheet, and we calculate the volume of that sheet. And we add them all up, you get the volume of that cylinder. Now let's say if we just slide that cylinder infinitely many times, or we just let the number of ring on that cylinder go to infinity, then the volume of that sheet is estimated to be the volume, is estimated to be the area, of this sheet that you just slide it out. Okay, and note that if you cut it up and slide it out, the outer layer, the layer here, the length of that layer is just the circumference of the circular base of that cylinder, and that circumference is 2 pi r. Okay, and the height of this cylinder is whatever that function f of x would be. Okay. So to calculate the volume using the cylindrical shell method, we say the volume is equal to 2 pi times the shell radius times the shell height. So 2 pi times the shell radius, so 2 pi r. The shell height is f of x. And we evaluate from A to B. Okay. Define R that the region bounded above by the graph of f of x equal 1 over x, below by the x-axis over the interval 1, 3. Find the volume of the solid generated by revolving R around the y-axis. So let's take a look at the picture. Let's make a rough sketch of what it should look like. The graph of f of x equal 1 over x, 1, 1, 3, 1/3. So this is the curve that we're looking at. And this is the region that is given. Now let's go ahead and rotate this about the y-axis. We should get something that looks like this figure. Okay. And it's got a have a kind of a hollow in the middle. Okay, so that is the figure that we are calculate the volume of. Okay. So let's take a look at this. When we draw this rectangle, we can see that the height of this figure is f of x. Okay. And the radius is x, and x is varied between 1 to 3. Okay, so we can calculate the volume. V is equal to 2 pi, and the radius vary between 1 to 3 of x times f of x, that is 1 over x dx, and this equal to 2 pi from 1 to 3 of 1 dx, that equal 2 pi x evaluate from 1 to 3, that is 2 pi times 3 minus 1, 2 pi times 2, this is 4 pi. Define R as the region bounded above by the graph of f of x equal 2x minus x squared, below by the x-axis over the interval 0 to 2, and we want to find the volume of the solid revolving R around the y-axis. Okay. Let's first get the region. Okay. So f of x equal 2x minus x squared, have the x-intercept at x equals 0 and at x equal 2. So 0, 2. And this is the parabola, so it gotta go something look like that. So this is the region that we will rotating about revolving around the y-axis. So we gotta get something look like that. So the volume is 2 pi times the radius x. X is vary between 0 to 2 of f of x. That is 2x minus x squared dx. And let's solve this integral. Simplify this, we get 2 pi times 4/3. So the volume is 8 pi over 3.